Welcome to the lecture series on time value of money, concepts and calculations. In this lecture we will cover annuity, annuity part 1 and annuity part 2. An annuity is a series of regular, equally spaced payments over a defined period of time, often called the term, at a constant rate of interest. The payments may occur weekly, fortnightly, monthly, quarterly or yearly. Annuities are classified into 4 categories. These are: 1. Ordinary annuity, 2nd annuity due, 3rd deferred annuity and 4th perpetuity. An ordinary annuity is an annuity where the regular payments are made at the end of the successive time periods. Example of annuities are regular payment to saving accounts, payment to superannuation fund, periodic payment to a person from retirement fund, monthly home mortgage payments, insurance premiums, straight bonds paying coupon payments. Now, let us see what are the definitions of different annuity. Ordinary annuity. In ordinary annuity, the equal payments are made at the end of each compounding period starting from the first compounding period. Annuity due. In annuity due, the equal payments are made at the beginning of each compounding period starting from the first period. Deferred annuity. In deferred annuity, the first payment is deferred a certain number of compounding periods. Perpetuity. Perpetuity is an annuity where the payment period extends forever, which means that the periodic payments continue indefinitely. In this lecture, we will deal with only ordinary annuity. Let us see pictorially what is an ordinary annuity. In this picture, here we see that the principal is put here at t equal to 0, and then we get the annuities at 1, 2, 3, 4 up to n, where at the n we can find out the future value of the sum of all the annuities. So, here n payments are made and there are n periods. From the cash flow diagram shown above, the future amount f is the sum of payments starting from the end of the first period to the end of the nth period. Observe that the total number of payments is n and the total number of compounding periods is also n. Thus, in ordinary annuity, the number of payments and the number of compounding periods are equal. Now, let us take the annuity due. In annuity due, we see that the first payment is made at t equal to 0 time, and then up to n minus 1 periods the payments is made, and the end of the nth period the final value is calculated. So, as indicated in the figure above, F1 is the sum of ordinary annuity of n payments. The future amount f of annuity due at the end of nth period is one compounding period away from F1. In symbol, f is equal to F1 into 1 plus I. Future amount of annuity due is f. Deferred annuity. Here we will see that the first payment is deferred to the end of the period of kth. In deferred annuity, the first payment is deferred a certain number of compounding periods. in the diagram below, the first payment was made at the end of the kth period and n number of payments were made. The n payments from an ordinary annuity as indicated in the figure. Now, perpetuity. Perpetuity is an annuity where the payment period extends forever, which means that the periodic payments continue indefinitely. Here we will see that at the end of the first period the payment starts and it continues every year or every time term up to the infinite. Now, let us see the derivation of annuity for annually compounding. Now, we can write down the S, that is sum future value of the all annuities payment made for ordinary annuity is equal to the annuity A into 1 plus I to the power n minus 1 plus A into 1 plus I to the power n minus 2 and so on and so forth, A 1 plus I plus A. Now, if I multiply I plus 1 with the left hand side as well as right hand side, this becomes S into 1 plus I is equal to A 1 plus I to the power n plus A 1 plus I to the power n minus n, so on and so forth, and my last term will be A 1 plus I. Now, we subtract these two equations, that is equation number 1 from equation number 2, then it becomes S plus S I minus S is equal to A 1 plus I to the power n minus A. So, this A S cancels out. So, S I is equal to A 1 plus I to the power n minus A, and if I take A common, then it becomes 1 plus I to the power n minus 1 and this I is divided. So, S is equal to A in brackets 1 plus I to the power n minus 1 whole divided by I. This gives us the formula to find out annuity for annually compounding. Now, if we place the value of S with P, so it is P into 1 plus I to the power n is equal to A in brackets 1 plus I to the power n minus 1 whole divided by I, then P becomes A into 1 plus I to the power n minus 1 whole divided by I into 1 plus I to the power n. So, it shows the present worth of annuity for annual compounding, where A is the amount of annuity per year, S is the future value of sum of all annuities, P present value of sum of all annuities, I interest rate per year and number of years the annuities are paid. Here the number of payments are equal to number of compounding years. Now, if we go for the derivation of annuity for discretely compounding, the amount of annuity is A and the sum of all annuity payments for discretely compounding is S is equal to A 1 plus R divided by M to the power m n minus 1 plus A in brackets 1 plus R divided by M to the power m n minus 2, so on and so forth up to A. In the similar manner, we multiply S with 1 plus R by M left hand side and right hand side, and then equation 3 and 4 is formed. Then we add up the equation 3 and 4, it becomes S into 1 plus R by M minus 1 is equal to A 1 plus R divided by M to the power m n minus A, and S is equal to this value, which is A brackets 1 plus R by M to the power m n minus 1 brackets close and whole divided by R by M. And if I replace the value of S with P 1 plus R by M to the power m n, then P becomes this. So, this is the present value of the annuities when compound is discretely compounding. A is equal to amount of annuity per period, S equal to future value of sum of all annuities, P equal to present value of sum of all annuities, R is equal to nominal interest rate per year, and R m by m is equal to interest rate per period, n is number of years the annuities are paid, and m is the number of periods per year. Here also number of payments are equal to the number of compounding periods. Sometimes only the effective rate per period, that is per month, maybe per day, is known. However, compounding for m periods at an effective interest rate per period is not affected by the definition or length of the period. For example, compounding for 365 periods, that is days, at an interest rate of 0.03808%, and for this if I find out the I effective, this will be 1 plus 0.0003808 to the power 365 minus 1, which comes out to be 0.149 and which is 14.9%. So, this is the I effective, that is effective interest rate is 14.9%, is the same as compounding for 12 periods, that is month per month compounding at an interest rate of 1.164%, and for this percent if I find out I effective, that is effective interest rate, this is 1 plus 0.164 to the power 12 minus 1, which comes out to be around 14.9%, or once at an effective annual interest rate of 14.9%. In each case the interest rate per period is different, but the effective annual interest rate is the same. If only the daily effective rate were given, the discount factor formula could be used with I is equal to 0.03808% and n equal to 365 to represent each yearly cash flow. Hence, equation derived for annuity compounded annually can be converted into annuity compounded per period by simply replacing I is equal to R divided by M and N by M into N. So, annuity for annually compounding is S is equal to P equal to 1 plus I to the power n is equal to A in brackets 1 plus I to the power n minus 1 whole divided by I. Now, if I replace I by R by M and this n by M n, then I get the annuity for discretely compounding as this P equal to 1 plus I is replaced by R by M and n is replaced by M into n. Here also I is replaced by R by M, n is replaced by M into n minus 1 and I is replaced by R by M. Now, derivation of annuity for continuously compounding. Amount of annuity A and the sum of all the annuity payments for continuous compounding is this: A plus A into e to the power r plus A into the e to the power 2 r, A into e to the power 3 r and so on and so forth, A e to the power n minus 1 r. Now, if I multiply this S into e to the power r, this becomes A into e to the power r plus A into the power 2 r, so on and so forth, and A e to the power n r. Now, if I subtract equation 2 from equation 1, so this is S minus S e to the power r is equal to S in bracket 1 minus e to the power r is equal to A minus A e to the power n r, which is A in brackets 1 minus e to the power n r. So, I can write down here S is equal to A in brackets 1 minus e to the power n r divided by 1 minus e to the power r brackets closed, or I can take negative common, this becomes A e to the power n r minus 1 divided by e to the power r minus 1. So, this gives you annuity for continuously compounding. Now, annuity factor can be defined like this: A by P R n is equal to A in brackets e to the power r n in brackets e to the power r minus 1 divided by e to the power n r minus 1, and this factor A by F r n is this factor, which is A into in brackets e to the power r minus 1 whole divided by e to the power n r minus 1. Now, the present worth is given with this formula: P is equal to A in brackets e to the power n r minus 1 whole divided by e to the power n r and in brackets e to the power r minus 1, and this has been derived from here, where S has been put as P into e to the power r n and the value of A is taken from here. Say value of S has been taken from here. Now, if you see the ordinary annuity, it can be divided into 3 parts: annually compounding, discrete annually compounding and continuously compounding. So, we have derived the formula for annually compounding, derived formula for discrete annually compounding and for continuously compounding. Now, this shows the ANSI functional forms for annuity. Now, capital recovery factor, this multiplies a single amount at a time 0 to give the annual rate of a series of n equal amounts, and this is called A by P comma I comma n, and is given by this I 1 plus I to the power n divided by 1 plus I to the power n minus 1. Now, this converts P to A, that means present worth to annuity, and is written like this: A is equal to P into this factor A by P comma I comma n. Then there is a present worth factor which multiplies the annual rate of a series of n equal amounts to give a single amount at time 0. So, this is represented by in brackets P by A comma I comma n, and is given by this in brackets 1 plus I to the power n minus 1 whole divided by I into 1 plus I to the power n. This converts the annuity to present worth. So, written as P is equal to A into P by A comma I comma n. Third is the sinking fund factor. It multiplies a single amount at n to give the annual rate of a series of n equal amounts. It is given by A by F comma I comma n. This is I divided by 1 plus I to the power n minus 1. This converts F, the final worth or final value, to A, that is annuity, and given as A is equal to F in the brackets A oblique F comma I comma n. The same ANSI functional forms of annuity for other factors. Future worth factor, this multiplies the annual rate of a series of n equal amounts to give a single amount at n years, is called F by A comma I comma n, and this is given as 1 plus I to the power n minus 1 divided by I. This converts annuity to the future value. So, is written as F is equal to A into this factor F by A comma I comma n. Then capacity recovery factor, this is for continuous compounding, multiplies a single amount at a time 0 to give the annual rate of a series of n equal amounts given by A by P, R and n. So, it is equal to e to the power r n in brackets e to the power r minus 1 divided by e to the power r n minus 1. This converts P, which is the present value, to annuity. So, annuity can be calculated as A is equal to P into A by P, R and n. You will see that the I has been replaced by R. So, this in the note you will see that in the ANSI form, the distinction between discrete and continuous compounding or discounting is the replacement of I in the discrete compounding form with R for the continuous compounding form, and that is why I has been replaced by R, and the last factor is sinking fund factor multiplies a single amount at n to give the annual rate of a series of equal amounts, and this is called A by f comma r comma n. This factor is shown like this, and the value is e to the power r minus 1 divided by e to the power r n minus 1. It converts the future worth to annuities, and annuities can be calculated with this, that A is equal to f and this factor multiplied by this factor means this quantity. Now, if you see the annually compounding problem matrix, so we have this equation, and here if you see the above equation, which contains 4 variables, can be solved to find out the value of a single unknown variable only when other 3 variables are known. That means 4 type of problems can be created out of it. Thus, 4 types of problems can be generated out of this equation. The problem matrix of this equation are shown below. Now, the first is that P is given, I is given and N is given. We have to find out A, and the equation is A is equal to P I 1 plus I to the power n divided by 1 plus I to the power n minus 1. What it does? It finds annuity when present value P, interest rate I and the time in years are known, and such type of problem is called problem A. The second type of problem, given are A, I and N, and we have to find out the present worth or present value P, and the equation is P is equal to A in brackets 1 plus I to the power n minus 1 and whole divided by I into 1 plus I to the power n. It finds the present value of the annuity when annuity A, interest rate I and time in years n are known. Such type of problem is called problem type B. Then problem type C, A is known, N is known, P is known. We have to find out the value of I, and the equation is P I 1 plus I to the power n is equal to A in brackets 1 plus I to the power n minus 1, and this finds the interest rate when annuity A, present value P and the time in years n are known, and such type of problem is called problem type C. Here we see that in the LHS and RHS, left hand side and right hand side, I exists, and that is why in such type of problems are solved by trial and error. The fourth type of problem is A is given, P is given and I is given. We have to find out the value of n, and n is given as n is equal to ln in brackets A divided by A minus P I whole divided by ln 1 plus I. In this problem, find the time of in years n where annuity A, present value P and the interest rate I are known. Such type of problem is called problem T. Now, let us take problems. Now, first we take the problem type A. This is example 3. What annual end of the year payment for 15 years is necessary to repay the present loan of 20,000 at annual interest rate of 10%. Obviously, the solution is, the formula is f is equal to p into 1 plus I to the power n, and A is equal to S into I divided by in the brackets 1 plus I to the power n minus 1, and hence from these two equations I can find out the relationship between A and P. A is the annuity, A is equal to P star, and this is the value, where A is the amount invested at the end of each year, F total amount due at the end of n years, P the principal or present value of investment and number of interest periods, I annual interest rate in percentage, and hence I, when I is used, I had already told you that it is used as a fraction. So, I divided by 100. Now, A is not known, P is known, it is 20,000, N is 15 years, I is 0.1. So, in this equation we put the value and find out that A is rupees 26 29.47. Let us see an different problem, which is problem type B. This example 5. If one agrees to repay a loan by paying rupees 5,000 a year at the end of every year for 5 years and the annual interest rate is 8%, then how much one could borrow today? Now, if we analyze this, we find that what are given? The value of A is given, that is annuity is given, which is 5,000. I, the interest rate is given, which is 0.08, that is 8%, and N, the value of years is given, which is N equal to 5, and we have to calculate what is the value of P. So, we will use a formula which relates A to P, and this is the formula which relates A to P, and if we substitute the values, then we find that this is equal to P into 0.25045,645, and from here I can find out what is the value of P, which is equal to 5,000, which is the value of A, 5,000 is the value of A divided by this quantity, and this comes out to be 19,963.55. Now, this is what we have done through the equation which I have developed, but this can be solved by a second method from the first principles. So, let us see the second method. In the second method, find out the present value of all investments done at the end of each year. We are investing at the end of each year. On the first year, end of the first year, we are investing 5,000, end of the second year another 5,000, end of the third year another 5,000, end of the fourth year another 5,000, and end of the fifth year another 5,000. If I find out the present value of all these sums here, bring it to t equal to 0 and then sum it, so I will find out the results. So, let us see, when I find out the present value of this sum 5,000, which is been invested at the end of fifth year, this is 5,000 divided by 1 plus 1.08 to the power 5, and this 1.08 is equal to 1 plus I divided by 100. So, this will generate a present value of 3402.92. Similarly, this value, that is which I have invested at the end of fourth year, will generate a present value which will be equal to 5,000 divided by 1.08 to the power 4, and the present value is this. Similarly, the present value of the third year, this value and these values are computed and written here, and when I sum them up, it becomes 19,963.55. So, we saw two methods, one quick method and the other method which works on first principle, but gives you a very clear view how what is being done is before you. Now, let us take a problem type B. This is example 6. Suppose you will retire in exactly 1 year and want an account that will pay you rupees 30,000 a year for the next 20 years. The fund will be depleted at the end of the 20th year. Assuming a 8% annual interest rate, what will be the amount you need to deposit now? When you say that what amount you want to deposit now, that means I want the present value or the principal value. So, if we analyze this problem, we find that A is given, that is annuity is given, which is rupees 30,000. The interest rate is given, I is equal to 8%. The value of N is given, which is 20, and what is required is P. So, I take a equation which relates P to A, and this is the equation. So, I know the value of A, and then I multiply with this factor, and my value of P becomes now 2,94,544.43. Another problem, which is problem type C. If one agrees to repay a loan of rupees 19,963.55 by paying rupees 5,000 a year at the end of every year for 5 years, find out under what interest rate he has taken the loan. So, if we analyze, we find that what is given is A is 5,000, I is unknown, N is equal to 5 and P is rupees 19,963.55. So, we use this equation which relates P to A through I and N, and this has left hand side and this has right hand side, and in both the side A exists, and hence such type of problems are solved through trial and error. From this expression, the value of I can be computed using trial and error as given below. My LHS is P I in brackets 1 plus I to the power n, and RHS is right hand side is A into 1 plus I to the power n minus 1. So, I take different values of I and calculate LHS equal to RHS. So, we see at I equal to 0.08, that is 8%, LHS equal to RHS, and hence the required result is 8%. Now, we see problem type D. Example 5. If we agree to repay a loan of 19,963.55 by paying rupees 5,000 a year at the end of every year for certain amount of years, if the interest rate is 8%, find out the number of the year when the loan will be repaid. So, if we analyze it, we find that the A is given, that is 5,000, I is given which is 0.08, N is unknown, and P is 19,963.55. So, this is the equation which we have used to find out N, and once we put all the values, that is value of A, P, I, then we calculate, it comes out to be N is equal to 4.99999, which is equivalent to 5 years. Now, we have seen how A is related to P, and in this set of problems we will see how the A is related to FV, that is final value. There we have seen that A is related to PB, that is present value. Here we see how the A is related to the final value, and based on these equations what type of different questions can be created. So, this is the equation which is taken into account. A is equal to Fi divided by 1 plus I to the power n minus 1. The above equation, which contains 4 variables, can be solved to find out the value of a single unknown variable only when other 3 variables are known. Thus, 4 type of problems can be generated out of these equations. The problem matrix for these equations are shown below. So, if you see here, if F I n are given, then A has to be find out, and the equation is A is equal to F I divided by 1 plus I to the power n minus 1. So, here we have to find out the value of A, that is annuity, when future value F, interest rate I, and the time in years n are known. This type of problem we will call it problem E. Then given A I n, we have to calculate F. So, F is equal to A in brackets 1 plus I to the power n minus 1 divided by I. So, this formula will be used, and here find out the future value F when annuity A, interest rate I, and the time in years n are known. We call such type of problem problem type F. The third type of problem is that A is given, N is given, F is given. We have to calculate I, and this is written as F I is equal to A 1 plus I to the power n minus 1. Here we see that in both the side I exists, and hence such type of problems will be solved by trial and error by equating left hand side to right hand side. So, here find the interest rate I when annuity A, future value F, and the time in years n are known. Such type of problem will be called problem G. The last type of problem where A is given, F is given, and I is given, we have to calculate the value of n, where n is given by this equation, where n is equal to ln Fi by A plus 1 whole divided by ln 1 plus I. Here find the time in years n when annuity A, future value F, and the interest rate I are known, and this type of problem will be called problem H. So, we start with the problem E. How much one should invest at the end of each year for 10 years to get rupees 20,000 at the end of 10 years with the annual interest rate of 10%. The solution is, we have to pick up a equation which correlates A and F. So, this is the equation where A is the amount invested at the end of each year, F is the total amount due at the end of n years, n is the number of interest periods, I is the annual interest rate in percentage, I is equal to I by 100, and in the for the present problem A is unknown, F is known, n is known and I is known. So, we put up in this equation. So, the A comes out to be 1254.91. We take a mixed problem, problem E, mixed type. If a 40-year-old student wants to start saving for retirement and saves rupees 5 a day in her piggy bank, at the end of the year she invests the accumulated saving, which is 1825 in a bank, and expects an annual return of 9%. She will earn about 93,367.21 at the 60 years. However, if some other student starts his saving at 20 years under the same condition, gets rupees, this is 6,16,635.46 at the 60 year of age. How much must the 40-year-old deposit annually to catch the 20-year-old? This is the question, and what are given and what are absent, we see F is given 6,16,635.46, N is given 20 years, I is given 9% and A is missing, that we have to calculate the value of A. So, we use the equation A is equal to S into in the brackets I divided by 1 plus I to the power n minus 1 and find out the value of A, which is 12,053.04. So, the 40-year-old has to deposit 12,053 rupees 4 paisa at the end of the year for 20 years to catch the 20-year-old student. Now, take the problem type F. A 20-year-old student wants to start saving for retirement and saves rupees 5 a day in her piggy bank. At the end of the year, she invests the accumulated saving of 1,825 in a bank and expects an annual return of 9%. How much money she will have when she will be 60 years old? What is given here? A is given, which is 1,825, I is given 9%. So, we have to find out F. So, we pick up a equation which relates A to F as given below, and we put the values, and then we find out the F is equal to 6,16,635.46. We will see that I am using one type of problems, and by changing a little bit I am finding out the different parameters. This is to give you the clarity. Now, problem G, one is depositing 1,255 at the end of each year for 10 years to get rupees 20,000 at the end of 10 years. What is the annual interest rate? So, I had already told you that the interest rate problems, they will be requiring trial and error method. So, here F is given 20,000, A is 1,255, N is 10 and I value is missing. That means, we have to find out what will be the value of I. For this problem, F I is equal to A in brackets 1 plus I to the power n minus 1. So, LHS is F I, RHS is A into in brackets 1 plus I to the power n minus 1. So, we see that if we take I equal to 10%, LHS is almost equal to RHS, and if you see this, I is equal to 0.1, LHS is 2000 and RHS is 2000.147, they are almost equal, and hence answer is I is equal to 10%. Now, we take the problem H. One in depositing rupees 1,255 at the end of each year for n years to get 20,000 at the end of n years. If the interest rate is 10%, then find out the value of n. Here F is given 20,000, A is given 1,255, I is 10% and n is unknown. So, from the table 2 we can pick up the equation which defines n with other parameters. This is the equation and we put the values and we get n is equal to 10 years. Now, take some other problems of continuous compounding. What annual end of the year payment for 15 years is necessary to repay the present loan of rupees 20,000 at annual interest rate of 10% when continuous compounding is used. So, what is given to us in the present problem is A, P is equal to rupees 20,000, N is 15, I is 0.1. So, we use the equation here A is equal to P into e to the power r n in brackets e to the power r minus 1 divided by e to the power r n minus 1. So, this is used for continuous compounding, we have already derived this. So, if we put the values in these equations, the value of A comes out to be 2707.56. This is again another question on continuous compounding. How much one should invest at the end of each year for 10 years to get rupees 20,000 at the end of 10 years with the annual interest rate of 10% when continuous compounding is used. So, here what we want is A, and this factor A by f comma r comma n is known to us. So, we use this. So, f into e to the power r minus 1 divided by e to the power r n minus 1, we use this equation and put the values. So, A comes out to be 1224.14. Now, this is again we take a mixed type of problem. Mr. and Mrs. Sharma wish to have an annuity for their daughter when she goes to university. They wish to invest into an annuity that will pay their daughter rupees 2,000 per month for 4 years. What is the present value of the annuity given that current interest rate is 9% per annum? So, we have rupees 2,000, m is 12, interest rate per month is r by m is 0.09 by 12, that is 0.0075, number of periods is 12 into 4 because she is studying a course of 4 years. So, we have to pay per month up to 4 years. So, the number of periods is 48. So, we use this equation which relates P to A and put the values, and P comes out to be 80,369.85. This means if rupees 80,369.85 is invested now at 9%, will provide rupees 2,000 per month for the next 4 years. Another mixed type of problem we take. Mr. Misra borrows rupees 5 lakh to buy a car. He wishes to make monthly payments for 5 years. The interest rate he is charged is 10.5% per annum. What is the size of each monthly payment? So, obviously, we need the value of A, that is annuity, P is 5 lakhs, frequency of payment per year M is 12, that is per month we have to pay, interest per month is R divided by M, which comes out to be 0.105 divided by 12, it comes out to be 0.00875, and number of periods is 12 into 5, that is 60, because he has to pay for 5 years. So, we take a equation which relates A to P and put the values and find out that the value of A is 10,746.95. This means to borrow rupees 5 lakh at 10% 5% from bank, one has to pay rupees 10,746.95 per month for 5 years. Thank you, gentlemen.